So this part was not recorded, so that's why I think we were here. We discussed this part. Yes. We did not solve the problem. Yeah. Okay. So here we see cross flow heat exchanger. So a test is conducted to determine the overall heat transfer coefficient U, right, in an automotive radiator. So here we see a radiator, right? So radiator is a cross flow heat exchanger and both fluids are unmixed. And they measured these temperatures. Air is entering at 20, leaving at 40. Water is entering at 90, leaving at 65. Okay. That is a compact cross-flow water to air heat exchanger with both fluids unmixed. The radiator has 40 tubes. Okay. Here few are shown, actually there are 40 tubes. And each has internal diameter, di is given, and length of each one, 65 centimeters. So it means the cross-sectional area here is given. Surface area, I d L into total number of tubes, which is 40. Okay, hot water enters the tube, so water is flowing in the tube at this mass flow rate. So this is THI, THO, this is M dot H. Here, this is TCI, TCO. And M dot C is also given. Air flows at this, from this to this temperature. Airflow is mass flow rate is not given. Determine the overall heat transfer coefficient. So that's what they measured, and from here we can find out overall U. And it is mentioned calculate heat transfer coefficient UI based on inner surface area, because outer surface area would require the, and would also require the heat transfer area of Fen, unfen. Yes, efficiency Fen part. So here we are using UIAI delta T, not UO. So here is the equation. UIAI LMTT. UI we will find out. This is an experiment to calculate UI. You want to calculate HIHO here, right? So AI is given. Delta TLM is, that is, yes, this is cross flow. This delta TLM we can find out from the equation for counterflow, and you have to multiply with a factor F. That will be delta TLM for cross flow. So let's show it as counterflow. THI, THO, TCI, TCO. So that is delta T1, delta T2. Okay. So this is given as delta T1 minus delta T2. Okay. Now you have to multiply with F. So delta T1 is clear, delta T2 is clear. All the values are given here because those were measured.
How to get F?
Yes, now we'll see F. AI is clear. Q dot, yeah. MCP product is given for water side. This 0.6 kilograms per second is given for water. M dot H is given, so we can find out Q dot. M dot H, CPH, delta T of hot fluid. So only thing remaining is now F, because it's a cross flow heat exchanger. So for that we need to have those charts. Here is that chart. So here is that these are the two fluids. Okay, so you know now we can find out this factor and this factor. Okay, that is done here. That's what we have discussed. Okay, delta TLM as a pure counterflow. Actually, it's not counterflow. That's why we have to use this one. So here we need these two factors. So small t is for hot fluid, capital T for cold fluid. If we reverse it, we can check whether it will. Okay, anyways, P is 0.36 and R is, so 1 and 2 is simply inlet and outlet. Okay, so here we have these two terms. P is 0.36, where is P? This is P. 0.3, 0.4, 0.35. So now you can draw a line of 0.36. Okay. Second is R, 0.8. Here is the intersection. So draw a horizontal line to reach this F factor. So 0.95, so 0.97.
So he's saying single pass crossover.
Okay.
أزمة في الباس.
Good question.
Maybe it's like this.
Maybe another one here, double pass. Or this, maybe this air is again made to flow like this. That will be double pass, but we are not covering double pass cross flow here. Only single pass. This is single pass, so double pass means like this. The same air is again made to flow to transfer more heat. That's what I think the meaning of double pass cross flow. Okay, but normally we have single pass radiator. Okay. So now F is given. It's very near to, according to this data, it is near to 1, like a counterflow. Anyway, so now we can find out U on the basis of inner pipe. Okay, so that is a way to calculate U experimentally.
But if you want U on the basis of outer surface, how do we calculate it? Include the outer area, the whole?
The whole heat transfer area. Fan plus unfan, everything. Those should be given.
No factors. No factors for the area. So.
No. Just like, the simple heat transfer area, wherever the air comes in contact. Yeah. Total area. But equation will be Q is equal to UOAO delta T. So you will calculate UO. But UOAO will be equal to UIAI. Product will be same. So here area will increase, so UO will drop. UO will drop. This product will be same. Okay, any question? So now this is the only difference for cross flow and shell and tube type. We have these charts or charts to find out F factor to be multiplied with LMTD. LMTD here we are using for counterflow, pure counterflow, multiplied by that F. Okay.
So the charts are only for counterflow?
Yeah. Here, when F factor is multiplied with delta TLM based on counterflow, counterflow will give us a maximum possible.
So
Right.
the factors will be of all the system.
Yes, this factor has to be multiplied always with counterflow LMTD, not parallel flow. Okay, so now we have covered this part, LMTD method, to find out or to design heat exchangers. Okay. The second method, alternative of LMTD, where area is given. Area is given. And we want to find out Q dot and temperatures, exit temperatures normally, CO and THO. TCI and THI normally we know it. We know them given. These are actually the exit. So these are unknown. Area is normally given. We can use this same LMTD method, but there we have to do some more iterations. Because if we use the same UA delta T LM method, okay, where area is given, but here again you have these two unknowns, LMTD. So it means you will assume, you will solve it for Q dot, and then you will put Q dot is equal to M dot H CPH delta T of hot fluid. The same Q dot is equal to M dot C CPC delta T, and from here you will write an equation of THO, TCO, whatever you assume. So you will be doing iterations. We can use the same method, but here you need iterations. Okay.
So we define one temperature, one water temperature. We find it for Q equivalent.
Yeah, okay, yes. That is also fine. So, but we have another method, and this other method is very powerful concept. Okay, based on mathematical derivations. Because now the task is to find out the unknown heat transfer when area is given. Okay, so this is the second kind of heat exchanger problem. So we already discussed. So here is another method which was proposed by these two people, Case and London, in 1955, and that method is called effectiveness NTU method, which simplifies the heat exchanger analysis significantly. So we'll see now. Now here we see two more terms, effectiveness and NTU. So let's first define effectiveness of a heat exchanger. Just like efficiency of a heat exchanger. So how we can define this thing? Effectiveness represented by omega. So it is
With the heat exchanger against without it.
Without it, what means without? Is not a fin. Q actual over Q maximum in the same heat exchanger. Without heat exchanger, how to exchange heat without a heat exchanger? So Q actual over Q maximum. So what is Q actual? Let's see here. A counterflow heat exchanger, temperature profile is shown. What is actual heat transfer? No, the other one, fluid. This is actual heat transfer. I can write it in terms of hot fluid, in terms of cold fluid. TCO minus TCI. Here we should write THI minus THO. That is actual heat transfer. Now what is maximum possible? What look on this. Again, we are taking counterflow heat exchanger as our standard or reference. So what is the maximum possible? THI to TCO?
The maximum.
Yes, yes. If you increase this area, so what we can expect, this THO will become equal to TCI. So maximum possible temperature difference which is available in any heat exchanger is THI minus, yeah, that is the maximum possible temperature difference we can think of. So let's write here. Maximum possible temperature difference in a heat exchanger is THI minus TCI. Now we have to multiply with some MCP product. Now which MCP product?
Average. The maximum one?
Okay. Which fluid will result in maximum temperature change? Higher MCP product or lower MCP product? Lower. This is the maximum possible temperature change multiplied by MCP of the lower one. We are thinking about the maximum possible. So maximum possible delta T will be given by MCP, whichever is lower. It could be hot, it could be cold. So you should write M dot Cp minimum. Whichever is minimum, that is actually defining the maximum temperature change. MCP product
The minimum MCP product is the bottleneck.
is the bottleneck, or is the threshold, or yeah, many terms like this. Limiting factor. So whichever MCP is smaller, that must be multiplied here. So for a given heat transfer problem, you know MCP product of both fluids already. So which one is minimum will give us the maximum possible heat transfer. So that's how we define effectiveness, Q actual, either this or this divided by this term. So here we are defining a new term which is called effectiveness of a heat exchanger. Actual heat transfer is clear. Here M small p is written as capital C of a cold fluid or for a hot fluid. Okay. This is actual heat transfer. Just mathematically, we are defining which is given, which is not given, that comes later. Because on the basis of these definitions, they will develop equations. Okay, that is clear. Will reach heat transfer in a heat exchanger will reach its maximum value when cold fluid is heated to THN or THN is cooled till TCN.
So we have to.
Yeah, we can write in two ways. Okay, but we are writing in terms of this THI minus TCI because inlet temperatures are normally known to us. Right. So maximum possible temperature difference, we can write it like this. If these are not equal, heat capacity rates, then the minimum will decide the maximum possible heat transfer. Okay, that's what we have discussed already. So now we can write this is Q dot maximum given by C, capital C of minimum. It could be hot, it could be cold. Smaller of MHCPH or MCCPC. As an example, here he is showing this is the hot oil entering at this temperature. Flow rate CP, similarly cold water temperature, flow rate CP. So here I can define C minimum because MCP product of cold fluid, MCP product of hot fluid are given. Here is the hot fluid is as lower C minimum. Here is the delta T maximum, THI minus TCI. So I can find out what is maximum possible. C minimum multiplied by delta. That is the maximum possible heat transfer in this heat exchanger. If it has a infinite area or very large area. Okay, so this concept is clear. If MCP product is same, then anyone can be used. Okay. Means delta TH will be equal to delta TC. That's what we already know. Okay, now comes the real thing. Now we know how we have defined effectiveness. Okay, so from this definition of effect, just like in fin efficiency, I can write heat transfer efficiency is equal to heat transfer through a fin is equal to fin efficiency multiplied by maximum possible. Similarly, here I can write an equation of heat transfer, actual heat transfer, in terms of effectiveness multiplied by Q maximum. Okay, which is this one. So far, any question? Okay. So from here, if I know effectiveness, I can find out Q dot, and I can find out THO and TCO. All right. So this effectiveness is, again, of course, it is directly or indirectly depending upon the geometry of the heat exchanger, flow arrangement, parallel flow, because in every case you will have a different value of effectiveness for the same input parameters. Okay. So for a double pipe parallel flow, okay, for a double pipe parallel flow, we can derive this equation using these definitions. Q is equal to UA delta T. We will introduce UA delta T. We have these equations where we can derive this correlation. Effectiveness of a parallel flow double pipe heat exchanger in terms of C minimum and C maximum for a given U and for a given area, surface area. So this derivation is here for a parallel flow. It's not difficult. Here we know how we have defined. Now you're just playing mathematically. It's all mathematics and we can end up this equation.
NTU?
Yes, this UA over C minimum is named as NTU, number of transfer units. We also use that term in chapter 7, I think. So here you have this derivation, which was proposed by these two people. They come up with this idea. So this is for parallel flow. Similarly, we have for counter flow. And so on. Shell and tube, cross flow, they have developed. Yes, in every case, you will see this effectiveness as a function of this C minimum over C maximum and this NTU, UA over C minimum. They have developed these correlations for many heat exchangers, for different types of heat exchangers in this form. All these correlations you will see there, NTU and this small c. Small c, this is a ratio which is named as small c. C minimum over C maximum. What is C minimum? MCP product, whichever is minimum, hot or cold. And the other one is maximum. So here are the derivations which you can go through because they are not a part of exam, so I will not explain. So, and also we do not have time, but you can understand it very easily. It's mathematics.
It's not the same as parallel, but multiplied by a factor?
No, here it's a different thing. That was totally different criteria or a different procedure. Here it's a different procedure. There is no F. Every heat exchanger will result in a different equation of effectiveness, but they convert this equation in terms of these numbers. All these equations. Okay, so here these two are given. So here is for parallel flow. Here now we can introduce this number NTU and this one as small c, heat capacity ratio. Heat capacity ratio. Effectiveness. Look, in this equation normally we know U, and we are saying this method is applicable when area is given.
Yes.
So area, U, C, MCP product, we decide also given. So just put it there and find out effectiveness, and from the effectiveness find out heat transfer.
How do we know the impact?
HI and HO. For fully developed flows, MCP product is given, mass flow rate is given, area is given, so it means you know the configurations also. So we can find out HI and HO, find out U. If you cannot find, okay, do an experiment and find out U. Okay. Anyways, so this is for parallel flows. Similarly, here now he is defining these terms. They are naming it as NTU. Now NTU, look here in NTU, MCP product is normally fixed for a particular heat exchanger. U is also gets fixed. So it is all dependent upon area. Increasing the area will increase the effectiveness. You will see the charts, also the variation of area versus effectiveness. You can show it here for a given C minimum, C maximum, U and area. So that's what is it saying, that NTU is actually a measure of heat transfer surface area if U and C minimum are given. Higher will be the area, higher will be the NTU, and higher will be the effectiveness. Right? By increasing area, effectiveness increases. But maybe after a certain point, increasing area is not useful. You have reached the limits. Okay. Yes. So here, okay, these two terms, if you put them, so now in general, we can say effectiveness of a heat exchanger is only a function of these two. These two non-dimensional, yes, non-dimensional numbers. Yeah, those become non-dimensions numbers. Here you see a chart. A double pipe parallel flow, here is the effectiveness equation. Double pipe counterflow for C less than 1, okay, small c, C equal to 1, and so on for all others. In every equation you will see NTU and small c, that's all. The rest are just the constants which will be different for every case. This is N shell passes, 2N, 4N tube passes. So this N is representing that number of shells.
Out.
Okay. So now we'll discuss it, but this is a chart or a table of equations of effectiveness as a function of these two numbers, NTU and C. Okay, interesting thing is, yeah, I'll explain this thing, it's coming. What is C is equal to 0? So, yeah, we have a separate slide to discuss this thing. Okay, yes, you're right. We can write these equations here. These equations are written effectiveness as a function of NTU and C. I can write the same equations as NTU equal to a function of, then what this means, NTU is, it means this equation can also give us unknown A. If I write this equation in this form, we have a separate table there, they have the same equations, but NTU is unknown, is written on the left hand side and every other thing on the other. So it means when you want to design a heat exchanger from the scratch, area is unknown. What you choose, that my heat exchanger should have this much effectiveness. So you are saying effectiveness is known to me. So then you can find the area. Which area will give you this much effectiveness? Yes, using the same equations, we just write it in terms of NTU. NTU in terms of effectiveness and C.
Is this mathematically solvable?
Yes, we have a separate table I will show you, where NTU is here and effectiveness and this. It's all mathematics now. It's all mathematics. So that's why I told you this is a very powerful concept which they come up. Right? Unbelievable.
You have something like this, but for H it will be very good.
H is there inside U.
For defining H, we have also only experimental.
Only experiment. Yeah, H is still so complex, especially in turbulent flow. Laminar, yes, you can develop mathematical forms, simple mathematical forms. Okay. Okay, so the same table, by solving it for a range of values, they have developed charts also. So what is this chart? To find out effectiveness as a function of NTU and C. Okay, now let's see what is this. C is equal to 1 and C is equal to 0.
Very large.
C is equal to 1 is clear. Both fluids have same MCP product, but C is equal to 0. C is equal to 0 means C minimum over, yes, C maximum, not 0, but approaching to 0. It means C minimum is, for example, 1, C maximum is, for example, 5,000. Then it is that thing which we are referring to. That other fluid has very high MCP product. And this will occur when small MCP product, very large MCP product,
Very large.
yeah, or C is very large. Okay, what about
The ratio of C.
boiling and condensation? If one of the fluid is boiling or condensation, there is no C. So we have to replace this thing with M into H. So this C maximum, let's represent it in the form of M into H product. Alright.
And when boiling, we have very large.
Yes, so this MCP product is very large, means you have H there. H is normally very large whenever the fluid is boiling or condensing. This is this case, actually. When you are here in thousands, but here this is very small. So when this will be normally when the other fluid is not necessarily very high mass flow rate, low mass flow rate, but very high H makes it a very large value. So that is this case. And you see here the effect now from here. Now this graph is for parallel. This one is for counter. Both are double pipe. And in all of these figures, you will see the C is equal to 0 will be highest effectiveness and C is equal to 1 will be lowest effectiveness.
For all different types of heat exchanger, for C minimum is equal.
C minimum?
Yeah. For C equal to 0, they are equal.
Yes. This is same for everyone. This is now 1 shell, 2, 4 tube passes. This is 2 shell, 4, 8, 12 tube passes. Same thing, effectiveness as a function of NTU. Here is the C, small c. This is for cross flow. Both fluids unmixed here. One is unmixed, other is mixed. Cross flow. But here in this particular figure, you see dotted lines also. Because here, what is the meaning of dotted line? Here it is specifically mentioned. These dotted or dashed lines, those are for the case when C minimum is unmixed and C maximum is mixed. If it is the other way around, then solid line. Okay. Yeah, there is a little difference here. As the NTU increases, there is a small difference. So that's why. For both unmixed, there is only one single line, but here you have two options. Which fluid is unmixed and which fluid is mixed? Minimum one or maximum one? Okay, so those equations, those are also presented in the form of charts.
the larger C, small c, we have like a upper limit for the.
Yeah, now let's discuss this thing in more detail. Here, for C is equal to 1, for parallel flow, counter flow, and cross flow with both fluid unmixed is shown separately here in one graph. Now we can make our understanding of it. Effectiveness as a function of NTU. So one thing is clear, as the NTU is increasing, effectiveness is increasing. But after a certain point, maybe after 3, the change is not that significant, especially for parallel flow. Even after 1, it becomes sustained. This is one observation. Second observation, we see that parallel flow will give you the least effectiveness. Highest will always be same double pipe but counterflow, and all others will be between these two. Counterflow will give us highest effectiveness, parallel flow will give us lowest effectiveness, and all others will be between these two. This is the second observation. Third observation, for very low NTU values,
Very low effectiveness.
whatever is the heat exchanger, same effectiveness. If A is very low, NTU is very low. NTU normally means area, because U and C minimum are fixed. This is another observation. And here this graph is shown for when all heat exchangers we are assuming C is equal to 1. The same is applicable for other values of C. Always counterflow will be highest, parallel flow will be lowest, and all others will be in between these two. What else we see here?
Why the top for C1 is we have the minimum.
What?
For small c equal to 1, you will have the minimum efficiency for any type. Minimum effectiveness for any type to occur at c equal to.
At C is equal to 0, you will have highest because one of the fluid is evaporating or condensing.
Okay.
C is equal to 0 means very high MCP product for one of the fluid.
If it was 1.
Both are same. Both are same. Both MCP product are same. But as you increase, so one of the fluid is responsible for high H, you can say. This high H is actually affecting you. All right. C is equal to 1 also means same delta T for both fluids. Change in delta T for both fluids is same. One of the C is lower, it will give you higher delta T. Yeah, so many things. Yeah, so all these factors they have grouped in mathematical form, effects. Okay, what else we can see here? And also it means NTU greater than 5. No need. Yeah, it seems like it is still increasing, but maybe it is increasing your cost drastically than the effectiveness which we are getting. Okay. Yeah, after below 0.3, effectiveness is same for any type of heat exchanger. Okay, C is between 0 and 1. Yeah, I think every point this we have already discussed. Whenever there is a phase change, C maximum is approaching to infinity. Okay, all of these effectiveness correlations will reduce to single equation if C is equal to 0. All of those for any heat exchanger. Yeah, those mathematical equations, just put C equal to 0, all of this will reduce to this form. But C is equal to 0 is 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 something which we are kind of assuming, that one fluid has infinite MCP product. Infinite. Now, what is 1 over infinite? Okay, so very large. So, for all heat exchangers, when we say C is approaching to 0, we should not say C is equal to 0. Approaching to 0 will get maximum possible effectiveness, whatever is the type of heat exchanger. Whatever is the type of heat exchanger.
So if I have, let's say, I should choose the lowest cost heat exchanger.
Yeah, that is a separate thing to select the type of heat exchanger. But here, theoretically, or just on technical basis, this is what we see. That's why in this refrigeration and air conditioning systems, the inside one is evaporator, because one of the fluid is evaporating. Outside one is condenser. One of the fluid is condensing. So one of the fluid has very high MCP product compared to the other one. Okay. In boiler and condenser in steam power plant, one of the fluid is changing phase.
Okay. Have the
highest effectiveness. That will result in the highest effectiveness also.
And beyond that is
It's already reached 1.
Yeah.
But this is theoretical. Actually, of course, you will not have C is equal to exactly 0. All right. Okay. So this is the table which I was referring to. NTU can be written in terms of effectiveness. All right. So now we can find the area even. If we say that effectiveness should be at least 0.8 or 0.7 of my heat exchanger. So we can even find the area. Again, Case and London, this is the reference where we can see all these. Hopefully the mathematical part is also given there.
We can cross-check our LMTD method. So
yeah. Yes, we can check, definitely. And those have been checked, don't worry. And that's why those are in the books, in the textbooks, these things. Okay, so the previous table gives us effectiveness when NTU is known. This table gives us NTU when effectiveness is known. C is definitely known to us. The specific heat ratio. These are the conclusions. It's not that difficult when to use LMTD, when to use effectiveness. Let's do one problem. Last problem. Now this problem we'll solve using if this method, effectiveness NTU method. It's very simple because now we have those developed equations, charts. Things becomes very easy. So here we see a shell and tube type. How many tube passes? Yes, 1, 2, 3, 4, 5. You already counted 6, 7, 8. It's written also. I thought it's already counted. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is one shell and 8 tube passes. Oil is entering. Inlet temperature, mass flow rate is given. Water entering. Inlet and outer temperatures are given. Area is given.
Only inlet.
Yes, only inlet. So it means the unknowns are cold fluid outlet temperature, hot fluid outlet temperature, and Q. Area is known. The heat transfer area is what? Yeah, the tubes are thin-walled and are made up of copper with an internal diameter of 1.4 centimeter. These pipes.
You already asked me which layout.
Yeah. The length of each tube pass is 5 meter. Length of each tube is from here till here. Then 5 plus 5, so 8 into 5. 40 meters. So in other words, area is given. Overall heat transfer coefficient is also given, U. If it is not given, then you will find out from HI and HO. Okay, so here U is given on the basis of inside area.
They are equal. Approximately. Thin wall
Yeah, here it's equal. Otherwise, wall
and wall.
dimensions would be given. Water flow rate MC is given, MH is given. Okay, inlet temperatures are given. So we can find out the heat transfer. We need to find out the heat transfer, which we can find out from effectiveness
Q max.
as a function of NTU and C. That will give us Q dot.
No,
And
difference is function of it.
Q dot we will find out from effectiveness, and effectiveness is equal to Q dot over
Q max.
Q max, and what will be Q maximum is equal to
MCP minimum.
yes MCP, whichever is minimum. THI minus TC I. Not simple delta T. THI minus TCI. Or delta T maximum. Okay. So once you know Q, find out TCO and THO, MCP delta T of hot fluid, MCP delta T of cold fluid, and find out TCO and THO. All right, that is done here. We need to find out.
It would be like 70.
Hmm?
70.
So here is the stoichiometric. Q dot we will calculate from effectiveness, effectiveness from NTU and C minimum. These are the equations to calculate Q dot, to calculate outlet cold temperature, outlet hot fluid temperature. CH is clear. MCP product of hot fluid, MCP product of cold fluid. These are given. M dot H, CPH of hot fluid, M dot C, CPC of cold fluid. Which one is minimum of the hot fluid? All right, so now we also know the ratio which will be used. Okay, so here is the Q dot maximum. What values? So that is the maximum possible. Actual will be less than this. 83.1 kilowatt.
What is NTU? NTU?
Yeah. So surface area for NTU, I need UA over. So here is the area.
So what is the word for NTU?
What is the
Words in
number of transfer unit? I don't know what is the logic. Number of transfer units, NTU. So if U is given, area given, C minimum given 0.84, 854. Go to the chart. Now, what is this type of heat exchanger? It was one shell and 8 tube passes. So any multiple of 2. Okay. So number of NTU we have 0.8. This is 0.5, 6, 7, 8, 9. Okay. Make your guess. Best guess 0.854 and small c is 0.76, 0.75.
0.75.
Yeah, 0.76. This is NTU. Otherwise, you have the table of equations. If you're,
this one.
yeah, this is easier. Okay. NTU and C. Here is NTU and here is C 0.75. So 0.7 somewhere here. 0.76. So here is the effectiveness. How much it is?
45,
46.
47.
Okay, 46 or 47. Let's see what is in the book. 47, 0.47. So find out Q This is Q maximum. So actual Q is only 39. Maximum possible is 83.1. So TCO and THO. Here pointed. To increase this, increase the area or increase the U, right? Increase the area or increase the U. This is kind of fixed now. We know which fluids are used. So U and A can increase the effectiveness. Okay.
So,
And you?
for calculating the temperature, should be Celsius plus Celsius.
There is delta T. Okay, you want 273, add 273 here, add 273 here.
No,
لا اللي يمين
I mean,
factor ده.
it's like unitless,
Dimension.
Which one?
dimensionless.
Q.
The second term.
Q.
So it should be dimensionless, but we are calculating. Temperature we are calculating. What is this equation? Temperature. So this is temperature plus, this must be unitless.
Should be in terms of
Yes,
temperature.
kilowatt will cancel. So at the end, that's what we are calculating.
No, it should be in terms of temperature.
What?
I'm trying to see.
What is this equation? This equation I have. This.
ما بتستحمل ال HC ما Celsius.
Yeah, MCP product. MCP product. That is kilowatts or watts.
في temperature بتطلع
Okay.
كيلو اه. مو فيها temperature. كيلو.
Okay, so here is a general criteria to select heat exchangers. It depends upon, of course, Q dot, main thing, cost, procurement, maintenance, and power requirement, pumping power, size and weight, type, materials. There are so many things which will be, and of course, leak tight, safety, reliability, quietness, so many things which not just the technical part, we have to see all this in combination to decide which type for which application. Okay. This is called unitary type or split type air conditioner, this one. But within this room, but when you switch on, compressor is outside. That's why the noise is less. But still, when the fan is running, it's quite noisy. Okay. So there is another type of heat exchanger system which is called radiative cooling. If on this entire wall, I have this radiative cooling. It is named as a radiative cooling, and here you have outside the cold fluid. Here you have the whole refrigeration system which is making this water to cool, and this water is just flowing into the room. But now you are using natural convection, which you do not want to have a fan. Okay, you want silence. So a long tube, a very large area, because convection coefficient is so low. So one of the group will be presenting this one and this radiative type cooling. Okay, they make a small cabin with this. So cold water is outside, simple pump is making this cold water to flow. That is called radiative cooling. Or it's radiative heating that is very common in West. Heating. Here you have a boiler.
The whole house is.
The whole house. Here is a boiler. Inside the room you have a radiator unit. That is called radiator unit. Only cold water is, hot water is flowing inside, which are installed with the wall, the big radiators in the Western countries. Okay.
The wall looks like an insulation. The wall.
They are not direct, yes, not just a wall. Over the wall, you have a metal sheet. Over this metal sheet, you have this pipe welded. Okay.
So the wall itself looks like a.
No, wall is at the back side, the front side, which goes to this room. This room air should come in contact. And also this radiation heat exchange. is at low temperature, we are at high temperature. So there is a radiation heat exchange plus there is convection. Okay, so you will eliminate this noise, but both have their own advantages, disadvantages. But here you should have a separate complete wall or complete roof.
More expensive.
It's difficult to say expensive because this is being used in large buildings, radiative cooling. Yeah, the whole roof is filled with these pipes when they are making. Okay. Or the floor, even you can have this thing on the floor. Okay. No, these are not so many because this is one problem, right? This is one problem.
Also,
Okay.
3 units.
So these are the practice problems. Now, if you can solve all these problems within the slide, they are of same difficulty level. All right. They are not of same difficulty. I have selected those of same difficulty level. So many of these we have already solved, but some of them which are not solved, these are practice problems. Derivations I already told you from this chapter.
Something I didn't understand, but how did we find derivations